So, very good morning. In the previous lecture, we looked at what a quasi-equilibrium process is and why is it important for us to sort of make that assumption of the process being quasi-equilibrium. And quasi-equilibrium does not mean that the process is reversible. In thermodynamics, reversibility has a very different connotation from what we regularly use in our practice. So quasi-equilibrium is more of referring to the mechanical equilibrium between the external surrounding and the actual boundary process that is going on in this particular case, of course. All right. So now let us move to the different properties. So let me make a new page. But before we go there, some of the units. I mean, you all know this, but just for completeness, the unit of mass, kilograms, unit of volume, liters, meter cube, dm cube, centimeter cubed. Then what do we have? We have various things like pressure. The units are kilopascal, megapascal. There are non-SI units such as bar, atmosphere. Okay, so anyway, okay, let's do this. So let's go into the properties. The first property that we need to know is the energy. And so what actually comprises the energy of a system? Okay, so energy is actually contained in a system. It is contained in a system. And microscopically, it is sort of the manifestation. So energy is the manifestation of the energies held by molecules, atoms, etc. So imagine you have okay, so let's say you have a monoatomic gas. So the energy held by this will be solely due to translation in 3 directions, and it can be rotation. And actually the rotation will only contribute to one sort of energy because the rotation is going to be invariant. And hell, even translation, it's going to be contributing to only one. So it can only have 2 contributions. A monoatomic gas can have only 2 contributions, that is translation and rotation. So if it does not interact with the other gases at all, which is true for ideal gas, then the total number of molecules in a system, so suppose a system has 1 mole of gas, that is 6.023 10 to the power 23 molecules of gas, and each of them, is rotating or translating at a certain velocity, then you can say that on an average per molecule, this is the energy that I have. It's literally half mv square or half I omega square. And then you say that these many molecules have this much energy. Fine. So this is in the absence. This is in the absence of any intermolecular attraction. So what do we mean by intermolecular attraction? You have what we know as the ideal gas corrections. And I'm talking about ideal gases, but in general, it is true for anything in general. Suppose you have 2 molecules like this. Ideal gas says that they don't interact, meaning they can collide, but they will just bounce off, no problem. But in reality, depending on the distance between these 2 centers, there will be a potential acting between each of them, which gives rise to various kinds of interactions. So we now know them as van der Waal interactions. And even at a smaller scale, there can be various other interactions as well. London forces. So London van der Waal, they are all clubbed together. So if this interaction is also there, then there is a deviation from ideality, and there are more energies which contribute apart from translation and rotation. Okay, so you have the contributions from intermolecular forces. Then you have molecular kinetic energy. Then we have intramolecular energy. So we've discussed about the intermolecular forces, which is the van der Waal or the London forces. The molecular kinetic energy, the entire molecule is moving with certain velocity. What do you mean by intramolecular energy? So suppose we forget this dumbbell shaped molecule. Let's directly take a molecule which is looking like this. So now this entire unit, center of mass, can be moving at a certain velocity. Now that velocity will be considered towards the molecular kinetic energy. Now what do you mean by intramolecular energy? When these bonds also start vibrating, or this bond, it can change its length, it can vibrate in this direction as well. So this angle can change, this length can change, and in fact it need not be even planar. So suppose this is the plane, this is one molecule, this is the other. Okay, well, two vectors will always form a plane. If you have something, say, which comprises of four molecules, these are out of plane. This can go towards the plane, this can come towards the plane, and again go away from the plane as well. So all such modes which are not per se related to the movement of the center of mass, they are all clubbed together in the description of the intramolecular energy. And so all of this, the culmination of all of this, is in the form of internal energy. This is how you define the internal energy of the system. And basically the way to go from such molecular level description, the way to go from this molecular level description to the macroscopic observable of energy is done through statistical mechanics or statistical thermodynamics. And there are some good books, Sears and Salinger. I'll just mention one of them. Those of you who are inclined towards good old physics. So now what happens? I mean, physically, when you have a system, say you have a pan of water, and then you're heating it. You're heating it. So slowly these modes, they become, they start getting more energy and they start vibrating even more. So molecular kinetic energy increases, intermolecular forces does not change all that much. The intramolecular energy, that component increases drastically because of the vibrations and oscillations. Okay, that is how you get transformed into steam. When you start taking away the energy, you're taking away each of the modes energy, and these higher order modes, which are the bond angle changing, the length of the bond changing, they start to go away. And finally, at 0 Kelvin, you know that all of these energies vanish, which is true only for a crystal, by the way. All right. So now let's move on to the next property, which is known as the specific volume. We briefly looked at this. specific volume slash density. Now, suppose you have, I mean, those of you who did attend my fluid mechanics class last semester, they will know what I'm going to talk about. But even for those of you who did not, in your respective sections also, it might have been covered. And it comes from ideas of continuum mechanics, continuum hypothesis. So suppose you have a big volume, say, of, which is designated by capital V, and there is a certain mass of liquid or refrigerant or anything. It doesn't matter what it is, but it occupies this entire volume. That is more important. If I just take the largest volume possible, and if I define the density as the mass over volume, alternately I can define this specific volume as the total volume over the mass. I have a property of this entire system. Okay, I have what I will say a macroscopic property. Now the question is this density or the specific volume? So I'll just quickly point out that the specific volume is simply 1 over density. Okay, so the question is this property, density or specific volume, only a macroscopic volume? Can I not measure it at each point in the domain? Is it possible for me to measure it at each point on the domain? Say I halve the volume. Even for this volume, if I take, so now it's going to be V by 2, most likely it's going to become M by 2. So it's going to give me the same density, because density is going to be M by 2 over V by 2. So this 2 cancels out. I'm going to get the same density. Correspondingly, I'm going to get the same specific volume, because it's going to be volume by 2 over mass by 2. So 2 cancels out, I get the same specific volume. Now even if I make this half, I'm going to get the same density and specific volume. If I make it half, how long can I keep halving this? I can keep halving this until I reach sort of the length scale, okay, where the mean free path of the particular molecule becomes comparable to the dimension of the volume under consideration. Okay, and it could be some factor times the mean free path, maybe like 10 or whatever. But the point is, beyond a certain length, you're not gonna get any significant variation. So if I were to plot the differential volume, so if I call this volume the differential volume delta V, plotting it on this axis, and I'm plotting the delta V over delta M, which is specific volume. So for very large volumes, you will have some macroscopic variations, because see, this volume may have some overall larger mass than this, owing to some prevalent physical condition. Or so for example, this room is receiving sunlight from the top, so the top density will be lower than the bottom density, for example. So overall, for very large volumes, you will have some nominal macroscopic variations. You will have some, but more or less you will get a good estimate of the volume. Some macroscopic variation, then it will, as we are reducing the differential volume, you will get remarkably stable. Then suddenly there will be a lot of fluctuations, because at this point, the volume has become so small that the number of molecules inside that volume, they are not stable. The moment one molecule goes in, maybe 3 molecules go out. Who knows? So in order for this to happen, you must have the length of this volume, this cube, to be comparable to the mean free path. Okay, is whatever I've said so far, is it clear to everyone? If you need any clarification, just let me know.
So
Hello?
can you once explain mean free path?
Mean free path is the minimum distance a molecule will move before colliding with someone else. You wanted to know mean free path in this context or in general what mean free path is?
Yes, sir, in this context.
Okay, wait. Suppose the mean free path is only this much, meaning the the molecule is going to collide with many other molecules before exiting this volume. Okay, and because the mean free path is very small, the neighboring molecules. So you can say that if one molecule exits this volume, it is very likely that another molecule will enter into the volume because the amount of collisions taking place is so high, right? The length of the volume is so large compared to that small thing that you can be very sure that once this exits, something will enter. But now let's say the mean free path is very large. When can the mean free path be large? When the system is a rarefied system. So suppose this is one molecule, this is one molecule, this is one molecule. So this molecule needs to move this much distance before colliding with someone or this much distance before colliding with someone. But when this is traveling with this, maybe this itself has escaped, itself has escaped, and you are only left with one molecule in this entire domain. So if you were to find out the volume, the average density, initially you had three molecules, then the next time instant you have only one molecule, then maybe at the next time instant four new molecules they enter into the system. So suddenly density will become 5, then maybe it can drop to 0, then again 1, then again 3. So this is time, this is number of molecules. So that is why when you have the choice of the system of the differential volume with which you want to find out the averages, you really get this large variability which I have reflected over here. So beyond a certain differential volume length, you cannot do this kind of averaging and then you go into the molecular dynamics regime. Beyond this region, you are still in the continuum regime where you can say that molecules, I don't care about how the molecules look like. All I need to worry about is what is the grand property of those ensemble of molecules. I do not care about how each of the molecule is behaving. I will treat them as an ensemble. I will treat them as a continuum. Does that make sense?
Yes.
All right, so let's proceed. So yeah, like it's a very important property, specific volume. You will see time and again we will make heavy use of these properties in problem solving. I cannot emphasize how important this is. For at this juncture, you just need to know it is the total volume divided by the mass. So if you have, for example, a balloon, you have an example, you have a balloon, the volume of this balloon is 10 liter, and suppose 2 kg nitrogen is there, then you will say the specific volume is going to be 10 liter over 2 kg. Well, you cannot do it like this because you have to convert them into consistent units. So 10 liter is going to be 10 to the power. How many meter cube is a liter?
-3.
Is it?
-3.
Okay, so it's going to be 5 to the power minus 3 meter cube per kg. Okay, this is the unit of specific volume. All right, let's proceed with pressure. Everyone knows what pressure is. You've been facing a lot of pressure. Actually, everyone's been facing a lot of pressure. Atmospheric pressure is always upon us. But Apart from that, sometimes you also have some mental pressure. So, but pressure fundamentally, I mean, given that we have done the entire course on fluid mechanics, uh, it seems very odd to now define it in a very childish way, but it is, of course, the limit of the area going to zero, the force normal to the area. I mean, this is what we call as the I mean, I'm calling it a hydrostatic pressure, but hydro is more for water, but it's more of a static pressure. Meaning, if you have an area of like this in a certain fluid, it will exert a pressure normal to it. Okay, and it will try to be compressive in nature. It will not be tensile in nature. And the different units for pressure are, I mean, the most easiest way to do it is Newton per meter square, which is also called as Pascal. But Pascal is a very small amount of pressure. So typically you will deal with kilopascal or megapascal. And because Pascal is a very small unit, people used to deal with 1 atmosphere, because 1 atmosphere is a good reference value. Because under normal conditions, you have stuff at 1 atmosphere. But 1 atmosphere is literally 101.325 Pascal, which is 101.325 kilopascal, which is also 0.101 megapascal, right? So whenever in a problem you're not given the data, how much atmosphere corresponds to, I mean, this atmosphere corresponds to how much kilopascal, you should use this. This value should be known to everyone. Right? You should never say that I did not know how many pascals does 1 atmosphere correspond to. That's not a very good thing to say to anyone at any point of your life. All right, so next thing, what do we have? Temperature. And I'm not bothering with some of the problems where you do simple static calculations. I mean, those are very easy problems. You've done plenty of those in your course on hydro, not hydro, but fluid mechanics. Now we have equality of pressure, equality of temperature. So we come to the zeroth law of thermodynamics, which says that if body A is in thermal equilibrium with body B, and if body B is also in thermal equilibrium with body C, then the body A is in thermal equilibrium with body C. So what do you mean by thermal equilibrium? So by thermal equilibrium we mean that the temperature of bodies A and B, they become equal, so that there is no heat transfer between A and B. Heat transfer can be affected between A and B only when there is a differential in temperature between A and B. So if A and B are in thermal equilibrium, you know that they are at the same temperature. B and C are at thermal equilibrium, then B and C are also at the same temperature. With the help of this, you can conclude that A and C will also be at thermal equilibrium. As trivial as it sounds, there is no sort of concrete proof to it, and it is taken as sort of an axiom. Okay, and it sort of logically precedes the conservation of energy and the entropy principles, and therefore it has been given the designation of the zeroth law of thermodynamics. Okay, so now we will move on to the discussion of properties of a pure substance. So over here we've just finished the sort of chapter on some general concepts of control mass, control volume, isolated system, intensive property, extensive property, quasi-equilibrium process, some properties, energy, temperature, pressure. So now I will create a new file. and we will start with properties of a pure substance. And over here, I mean, you really must pay attention to this particular chapter, because here you will learn how to fetch different properties. It doesn't matter how you're fetching the properties. You can use a computer, you can use your iPhone, you can use your whatever it is. You can use a thermodynamic table, or you can literally look up a plot. Doesn't matter. But you should know how to figure out, given a certain set of properties of a substance, how to figure out the other properties of a substance. Okay. So let's begin. This is properties properties of a pure substance. All right. So in the previous chapter, in the previous discussion, if I may, we discussed with some readily, or some obvious properties that are always available to us. That is the specific volume, or the density, if you might. But we will not use density in throughout the study. Uh, it's not customary to use density in thermodynamics. We've seen pressure, we've seen temperature, and these things we have an intuitive feel that we can say that okay, this item is at a pressure of so much, at a temperature of so much, it has a density of so much. Okay, so but there are other properties beyond this which can be used to define various systems, and knowing the properties and the behavior of substances, is rather important throughout our studies, because otherwise we will not be able to figure out what kind of refrigerant should be used, or what kind of mass flow rate should be used. Okay, so there are a host of applications. In fact, almost everything will require you to assess what the properties will be. For example, the air conditioning system that we spoke about, right? So you have the indoor unit, and you have compressor, then that is going to the outdoor unit, which has a throttle valve. Okay, so now how do you know what kind of refrigerant should you take? So suppose you want to maintain the room at maybe 4 degrees Celsius. Can you use the same refrigerant that you use in your room air conditioner? Obviously not. You must make a choice. You must make various design choices. So the compressor will compress to very high pressures. So then that puts a limit on how thin your copper can be, the copper tube can be. Okay, you cannot make it very thick, otherwise it will become very heavy. If the if the swing between the two pressures, so this is gonna be after throttle valve, it's gonna be the low pressure line, and after compressor, it's gonna be the high pressure line. If the difference between these two pressures is very high, the compressor power will be very high. And what decides how low this pressure is going to be? That is solely determined by the property of the particular refrigerant that we are going to choose. As a designer, as an HVAC designer, for you, the only thing available will be okay, look, I have to maintain my room at this much temperature, and continuously I will be losing away so much of cold. So the exfiltration of heat, maybe it is at the rate of exfiltration is maybe 500 watt. You have to maintain the room at 4 degrees Celsius and account for 500 watt heat losses. So why will there be heat losses through the room? Anyone who can tell? From intuition.
So as we need temperature very low, so to lower down the temperature, we need to extract much more heat. That's all.
No, so basically the answers, I mean, it's not a scientific question per se, but see, more like if the chamber is kept at 4 degrees Celsius, you will make the chamber like this, right? There will be always some amount of leakages from the doors, from the seals, and the door thickness will be finite. It cannot be infinitely thick. So heat will be, so suppose outside is 30 degrees Celsius, inside is 4 degrees Celsius. So slowly heat will come in. It will take a lot of time, but slowly heat will start coming in. Okay, so if you start off with a system like this, eventually this 4 degrees Celsius will start rising, and it will, after a very long time, it will become 30 degrees Celsius. It will come into equilibrium with the outside air. So this kind of thing, it's called as the, or rather, I mean, I've written it exfiltration, which is wrong. It's gonna be the infiltration of heat. Exfiltration of cold, but infiltration of heat. So the heat is gonna go in at this rate. So meaning you have to extract this much amount of heat. Okay. For example, in a refrigerator, you maintaining at 4 degrees Celsius, say the milk zone, whatever you call it. Someone is opening the fridge, someone is closing the fridge, some vegetable is absorbing more of the cold than the others. Okay, stuff like that keeps on happening. So you need to sort of always have accounting for this kind of heat transfer requirements. Of course, when everything becomes cold enough, when there is no more infiltration of heat, then you will see that the compressor switches off automatically by means of a thermostat. Okay, so this kind of designing, you will really need to pinpoint what the property of the substances are. All right, so I've mentioned that we are going to study the properties of a pure substance. So the first thing we need to do is define what a pure substance is. So pure substance is something which is homogeneous and which has invariable chemical composition. Okay, but it may exist in multiple phases. But despite existing in multiple phases, the chemical composition must be equal. So what do we mean by homogeneous? That in space, for a given phase, when we say homogeneous, say suppose this is ice, this is water. Wherever that phase exists, the properties are uniform throughout this. Similarly, for invariable chemical composition, the chemical composition throughout this will be equal, that is H2O. It can exist in multiple phases, so it's existing as ice, is existing as water. And again, homogeneous meaning even in ice, the property is going to be homogeneous throughout the ice. So basically some examples of this, a mixture of water in liquid state and water vapor. That's a pure substance. Now tell me this, is air is air a pure substance?
No, sir.
Why?
So
Sir,
there
it
are
depends
different
upon the
chemical
scale
substances
on
as
which
well,
we are
oxygen,
observing.
carbon dioxide.
One by one.
So there are different chemical substances in air, nitrogen and oxygen.
Very good. So we cannot consider air to be a pure substance. Why? Because it does not have an invariable chemical composition. Yes, that's what you wanted to convey, right?
Yes, sir.
All right, good. But, and there's a big but in the middle, in analysis that will be there later on, we can consider air to be a pure substance. Why will we consider it to be a pure substance? Because when we are going to study air, we will not consider phase transition of air, meaning we will not liquefy air. Air as a substance will be compressed, will be heated, will be cooled, but at no point of time air will be liquefied. Air liquefaction, carbon dioxide gets removed from air first, then nitrogen gets removed, then oxygen gets removed. Okay, so all these different gases, they get removed from air when they are cooled. As a result of this, when we have actual phase change, the true composition of air will drastically change. But when we have only air being heated or air being compressed, it will always contain that 72% nitrogen, 20 point whatever percent oxygen. This will also contain that much amount of nitrogen, oxygen. So in our study, this is very important. In our study, wherever there is no phase transition, we can also consider air to be a pure substance. Okay? Is it clear to everyone what I just mentioned?
Yes,
Yes,
sir.
sir.
All right. Okay. So now we will come to yet another definition or yet another consideration, which is known as the simple compressible substances. Okay, a simple compressible substance is something uh, where surface effects, magnetic effects, electric effects, they are all insignificant. The most significant thing will be due to compression. So that is why this compressible substance is there. Okay, things on which only pressure can act and influence and exert an influence. All right, so let's proceed. I mean, this also would have been quite obvious, but there is another entire area of thermodynamics where you will deal with surface effects, where you will deal with magnetic effects, but this is not the place where you will do that. Now let's look at equilibrium in a pure substance. All right. So how much time do we have? Okay, 10 more minutes. Should we start with this? Yeah, okay, I think we can start. So let me draw everyone's favorite hypothetical experiment, the piston cylinder experiment. So you have this cylinder, and let me draw a piston. So let's say the piston is all the way down, right? And in fact, let me just copy this template. We will require no, in fact, let me just move this fellow. Let me just copy this. In fact, let me just keep both of these things over here. We'll need this. Yeah, okay. So this contains liquid water. And On top of this, there is a big weight that is placed. Okay. Now, say the system, this contains 1 kilogram of water, and the initial temperature is 20 degrees Celsius, and the piston weight and everything, it maintains a pressure of 0.1 megapascal in this chamber. All right. So what do we have? We have 1 kg of liquid water at initial condition of 20 degrees Celsius and 0.1 megapascal. Okay, very good. So now let us do this. Let us heat this arrangement. This is heated with the help of a burner. So now what will happen? The temperature increases and the specific volume will also increase. So what will it look like? So it will look something like this, where this is like the phase boundary. This will be liquid water. This will be water vapor. Okay. And so what has happened here is the mass of the water vapor plus liquid, obviously it will remain the same, 1 kg. The pressure is, how much is the pressure going to be? Who can tell? What is the pressure in of this substance gonna be? Water vapor plus liquid water. Will the pressure increase, decrease? What will happen?
Sir, remain same.
It will remain the same. Very good answer. It's gonna be the same because the pressure is because of this mass and this piston. As such, this loading has not changed, and so under equilibrium, why did we conclude it's gonna be the same? Because this heating is slow, and we recall that everything is in quasi equilibrium. So whatever external thing is, internally also it has to be maintained. So externally, if this much force is acting, this plus this, internally also the pressure has to be that much. Otherwise, if these two pressures were not to be equal, then there would be free movement in either direction. If the block plus piston were to have a higher pressure than the internals, then this piston will rapidly move down. Alternatively, if the water vapor plus liquid water pressure would be larger than the force exerted by the block plus piston, then the piston block arrangement would fly out. Okay, so that is why we say that the pressure is going to be the same. This is as a consequence of the quasi-equilibrium assumption. However, what happens to the temperature? You're heating it, so temperature will increase. So temperature maybe it can go from 20 degrees Celsius to anywhere between, say at this point it is 80 degrees Celsius. And it will eventually get heated to a point all the liquid water vanishes. Yes, there will be a point where all the liquid water inside vanishes. So what will happen at that point? The mass will still be the same, the pressure will be the same. And how much will be the temperature? What do you think the temperature will be?
It's 100.
It will be close to 100 degrees Celsius. Okay, very good. But in reality, it is 99.6 degrees Celsius. Okay, that's a small caveat, but I'm gonna let this 99.6 be here. Okay, so what does it mean? So it means that throughout this process, we have kept pressure constant and heat transfer has caused an increase in temperature and an increase in the specific volume. Okay. Now we define what is termed as the saturation temperature, and the saturation temperature is the temperature at which vaporization takes place given a certain pressure. Meaning that if I declare, if I call this Tsat, the Tsat depends on the prevalent pressure, and that pressure is known as the saturation pressure as well. Okay, so 99.6 degrees Celsius, the is the, what do I say? I mean, how do I put it? Yeah, so 99.6 degrees Celsius is the saturation temperature corresponding to a pressure of 0.1 megapascal. And we will see all this in well charted, in well documented plots. Okay. So if a substance exists as both, so I mean, let's again take a look at what has happened. If we were to plot the, how do I? Let's plot the temperature and volume. No, so this will, forget this. How do I? So we could have started the experiment. We could have started this experiment even at a lower temperature. We could go to the edge of liquid water, which would be almost at 0 degrees Celsius. Okay. So at a certain P saturation and T saturation, if material exists as liquid, we call it a saturated liquid. So saturated liquid would correspond to this thing at 0 degrees Celsius. Okay, and similarly, for this particular conditions, Psat and Tsat, this particular condition would be called as saturated vapor. This would be saturated vapor. And why is it called as a saturated liquid and saturated vapor? Because at saturated vapor, there is no liquid present, and at saturated liquid, there would be no vapor present. Okay. Now, there is a state in between, and this state will be very important throughout our discussion. So, we define something as the quality. So, the substance can exist partly as liquid and partly as vapor at saturation temperature. for a given saturation pressure. So we define quality X as the ratio of mass of vapor divided by mass of vapor plus liquid. Okay, so total mass basically. So when X equal to 0, what does it correspond to? The situation corresponds to what?
Only liquid, saturated
Saturated
liquid.
liquid. And when X equal to 1, you have saturated
Vapor.
vapor. And anything in between, you can have X belonging to anything between 0 and 1. So say, I mean, there are a host of complicated simple looking problems but difficult logics. We will come to those, and it will all depend on what X will be. Those are like trick questions. We'll come to those when we actually look at the plots. We're getting there. I mean, I've been building up to these plots, these tables, these problem solvings for a while, but it is important for us to just get these definitions out of the way. Otherwise, you will be, then I have to spend more time during the problem solving to define this. Okay. So,
One doubt, sir.
yeah,
So, like we define the boiling point of water as 100 degrees Celsius, then by 99.6 degrees Celsius we are taking.
that 100 degrees Celsius is not true. Okay. That is not correct. That is, so there is an entire, like the point where vaporization versus the prevalent pressure. So at a certain pressure only it will be like 100 degrees Celsius, and that will be almost at atmospheric pressure. So that is why you consider it to be 100 degrees Celsius. Okay, as the pressure increases, the boiling point also changes. So for atmospheric pressure, like 1 atmosphere, 101325, it is 99.6. Okay.
Okay.
But here in the problem, it was 0.1 megapascal. You should also consider that. It was not exactly 1 atmosphere. I think at 1 atmosphere, it becomes 99.8 or something, if I remember correctly. So yeah, so where were we? Let's try to make a plot. Let's try to
Sir,
make a,
excuse me, sir.
yeah.
Sir, can you please elaborate a bit on saturation pressure?
So the pressure at which both these phases will exist. So what happens is, between this and this, you are between this point and this point, you are sort of lying in the x equal to 0 to x equal to 1 domain. You are not changing phase completely. You will always have some liquid, or you will always have some vapor. Okay. So this is the entire saturation zone. Saturation zone goes from saturated liquid to saturated vapor. So whatever the pressures and temperatures this correspond to, they are called as the saturation temperature and saturation pressure. Well, this point will be the saturation temperature, but all the pressures are going to be the saturation pressures. So don't worry about if this seems a bit confusing right now. The curves will make it clearer. Don't sweat it at this juncture. It is only, the things will be most clear when we make the plot. So let me make a certain plot. If you have 5 minutes time, do you have another class now? Does anyone have a class now, or can I spend 5 more minutes?
No, sir, I don't have any class.
You don't have a class, right? We can make the following curve. say you have the volume versus temperature. So for a liquid, what happens? As temperature increases, the volume increases. The volume increases. And so this curve we're drawing for a fixed pressure. Okay, so basically we're doing the same experiment and we're not doing something very different. We are doing the same experiment. Where is it? We are doing the same experiment. Okay, so the pressure is kept constant. So for a certain amount of pressure, the volume increases, and then what happens? This is now water. So you started with some ice and it has now melted to fully water. So at this point you will say that I have x equal to 0. Now you're still heating it. So now what will happen? When ice became liquid, this ice became liquid. Now you're adding temperature, you're adding heat. What will happen?
So for some time it will be like straight line parallel to x-axis.
It will be straight line parallel to its axis, but the volume will still increase. Okay, it will be a straight line, but the volume will still increase. And this is what you identify as what? The latent heat. And how
Yes,
far it
sir.
will go? So slowly you are going from x equal to 0 to x equal to 1. So you're going from liquid to vapor, right? You're going from fully liquid. So this temperature where this transition from liquid at, so this temperature will be 99 point. Okay, I think I know the source of it. I wrote this juncture. This heating will keep on going for liquid water till it reaches 99 degrees Celsius. I think that's what. So once this liquid water entirely reaches 99.6 degrees Celsius, then part of it will start to vaporize. So in going from 99.6 degree Celsius liquid water to 99.6 degrees Celsius saturated vapor, you will have this X intermediate X values. Okay, so let me just show it over here. So you have heated ice to go to liquid water. Now liquid water is at 99.6 degrees Celsius. Now the volume will increase, but the temperature is not going to change because you are simply affecting how much phase is changing. So this is what you know as latent heat. Now latent heat will take you till steam, and once you get completely steam, you will have a very large change in volume for a very small change in temperature. Now let us repeat the same experiment. Now this experiment has been done at 0.1 megapascal. Let me do yet another experiment at say 1 megapascal. So at 1 megapascal, I will again heat ice so that it becomes just boiling water. I will reach, I'm drawing it as a very exaggerated diagram, and it will stay flat. So at 1 megapascal, I don't recall the value, I have to look it up, but it will be something like 140 degrees Celsius. Okay, and then this will happen. Then, so this curve is for 1 megapascal. So this temperature where the liquid just begins to boil, that is the saturation temperature, and it corresponds to a pressure of 1 megapascal. Okay, we say that this 140 degrees Celsius is the saturation temperature, which corresponds to 1 megapascal pressure, and so this becomes the saturation pressure. And similarly, you will have multiple curves like this. You will have multiple curves like this. Oops. And so if you draw all the locus, you can draw the locus of these curves and the locus of these curves. So this locus will be this saturated vapor line, and this curve will be the saturated liquid line. Oops. And there will be a point where the saturated liquid and the saturated vapor, they will merge, and that particular point is known as the critical point. Okay, I think we will discuss more over this, more on this later on. Okay, but what I will do is tomorrow I will again discuss this experiment and I will label some points A, B, C, D so that it will be clear.
Sir, I had a doubt.
Yes.
Sir, where you have mentioned x is equal to 0, how it is x is equal to 0? Because the water is at 99.6 degrees Celsius, right? So
And
there will be some vapors as well.
no, that's what. It is just at the point where you can see the first molecule of vapor coming out. You can have water at boiling point without creating steam. Because
Oh, okay. So I thought it was of the previous experiment. So initially we took like 20 degrees Celsius, no? So I thought.
no, that's what I wrote it below this, so it got confused. So even in the previous experiment, I will just rub this off because look, I'll just reiterate the previous experiment. You have some liquid water at 20 degrees Celsius. You keep heating it until you will keep heating the water. Nothing will happen. Some volume will increase until you reach 99.6 degrees Celsius. So the starting point of this experiment now is liquid water at 99.6 degrees Celsius. Okay.
Yes, I got it.
Now any more heat addition to this liquid water at 99.6 degrees Celsius will not lead to a further change in the temperature, because now that heat absorbed will be used for changing phase. Yes.
Yes, sir.
And that heat is known as the latent heat. So now at 99.6 degrees Celsius, you had liquid water. Now you will slowly get starting water vapor plus liquid water, then fully water vapor. And so you're going from saturated liquid at x equal to 0 to saturated vapor, which is basically at x equal to 1. And there are all these intermediate stages. All right.
Yes, sir. Thanks.
So the liquid will be saturated for all temperatures below 99.6 because it's liquid everywhere below that.
Pardon me?
So the liquid water, we call it saturated liquid at 99.6, or anything below that also will
No,
also be.
saturated. No. Okay, very good point. I would have discussed this tomorrow anyway, but since you've asked, this question is, do we call this entire thing as saturated liquid or only this point as saturated liquid? Is this your question? Precise question?
Yes, sir.
The precise answer is only this point is saturated liquid. This branch, because it lies below the saturation temperature, is called as the subcooled liquid. Okay?
Okay, sir. And what about the point when ice transforms to liquid, completely to liquid? And what will we
Well,
call that point?
that comes later. Similar to, so we are now in this entire study, we will be more focused on liquid and vapors only. In engineering, we will face those. So we don't worry about those at all. No, one more thing. You didn't ask me about this. Do we call this also such a, like your question? This is only the point of saturated vapor. This is the only point of saturated vapor. Then what is this?
Superheated vapor, I'm assuming.
Arre, I don't know whether you just answered it, but it is actually superheated vapor.
So it's subcooled, so logically it should be
So
superheated.
this is literally the correct answer. I don't know whether you
I
heard it
didn't
some.
notice before.
Wow. This is literally superheated vapor. Because anything at this temperature is saturated. So it is only this curve which resides inside this orange dome. Yes?
Yes, sir.
That is going to be the curve that resides inside the orange dome is the saturation line. And this locus, it gives you the set of points corresponding to different pressures who are at saturated liquid. This curve, it shows the set of points at different pressures who are at saturated vapor. Okay, very good.
Okay, sir.
We will discuss this again tomorrow. Hopefully, I'll be able to take the class tomorrow in person. It seems okay at the moment. All right. So all of you, if possible, please also install the demo version of EES. Okay. The demo version is something which I will be also using so that you will not be able to say that this guy bamboozled us. He is using a paid version and we are using a free version. That's not how it works. We will use the same version. Okay. So let me just quickly show you where that version is. Stop sharing. Start sharing. Where do I share my entire screen? Share screen. Just go to EES, F-chart software. Inside this, you will have a demo. You see this? Demo. Are you seeing this?
Yes, sir.
Yes, sir.
Click on demo. You will be taken over here. Just fill out your credentials, submit. You will be able to get a download. Okay? So it does have some caveats that you cannot save the file, you cannot copy paste, but that's okay. You don't need it. Okay. Once you, I mean, you can choose to use the commercial one as well, but for those at home, I'm doing this so that you never feel left alone. Of course, you can always arrange for a quote unquote not exactly legal copy, but that's not how we do it. Okay, guys.
Yes, sir.
So I guess I'll see you later. In fact, let me just turn off recording. Just a moment. Let me just turn off recording.